depends only on the component of the force that's parallel to the displacement. If the force is constant, we don't have to integrate. If the force is constant, we can just take the component that's parallel to the motion and then multiply by the distance. Technically, force is a vector. Displacement is a vector. We're multiplying vectors together, and it's not as simple as 2 times 2 is 4. There are 2 ways to multiply vectors together. This way is called the dot product or the scalar product. It's called the scalar product because you get a scalar answer. Okay. To write the dot product, we write our vector dot. That dot is a very specific function. It's not simply the multiplication sign times the d displacement vector. Turns out, if we go back to that other example we did, if we had a force, F, that was applied to an object that moved horizontally, D, then all we needed was the component of the force that was parallel to D. So all we needed was this piece. This was force cosine theta. That is a perfectly legitimate way to find the dot product. That is a solution to the dot product. Finding the F cosine theta gives you the component that's parallel to the displacement. Then multiply by the displacement, and you have your answer. That is a solution to the dot product. Turns out, if you have any vector, say some random vector A, dotted with some random vector B, the answer is always going to be the magnitude of A times the magnitude of B times the cosine of the angle between them. Because A cosine theta will give you the component that's parallel to B. Sometimes in a problem, it's not really straightforward what this angle might be. If you don't know the angle, you can't use this right here to find the work. It makes it a little more difficult. For example, let's say we had a force that had 2 newtons in the x direction, 3 newtons in the y direction, and 1 newton in the z direction. So it's off at an angle like this. And let's say our object's on an incline, so it ends up moving a total distance of 3 meters in the x direction and 4 meters in the y direction. So it ends up moving up an incline this way. So you have a displacement vector this way, a force vector this way. If you want to use this equation, you would need to know the angle between those two. And it's a little challenging to find angles in 3-dimensional space. But there's another way to actually do the dot product. F dot D means we're taking our force, dotting it with our displacement, so what we're doing is we're taking the 2 newtons I had, dotting it with the 3 meters I had. That means we're taking 2 newtons times 3 meters and I dotted with I. It's only the vector portion that you're dotting. We're foiling. Plus the 2 newtons times the 4 meters times I dotted with J. Plus 3 newtons, 3 meters, J dotted with I, plus 3 newtons times 4 meters, J dotted with J. displacement is -1 Newton times 4 meters, K dotted with J. Now I know this looks really ugly, but it's going to simplify very quickly. Dot product. Regardless of what vectors you're dotting, if you dot the two vectors together, you have to get the magnitude of the two vectors times the cosine of the angle between them. So for example, I dotted with I. The magnitude of I is 1, so we get 1 times 1 times the cosine. If I draw an I vector and another I vector, what's the angle between them? So cosine of 0 degrees is 1. I dotted with I gives you the number 1. J dotted with J will do the same thing, because the angle between them is 0. And K dotted with K will give you the same thing. What about I dotted with J, though?
0.
Exactly. What's the angle between I and J? Cosine of 90 is 0. I dotted with J is 0. That whole term's going to go away. J dotted with I, they're perpendicular. It's going to be 0. That whole term goes away. K dotted with J. K and J are perpendicular. That whole term goes away. Doing the dot product is really easy. The dot product is simply multiplying the parallel components. So you take the x component and multiply it by the x component. Then you add the y component multiplied by the y component. Then you add the z component multiplied by the z component. The displacement didn't have a z component, so we're multiplying it by 0. That's all you're doing. The dot product simply multiplies parallel components. You multiply the x's together, multiply the y's together, multiply the z's together, add it up, that's your answer. So we have 6 Newton meters, which is a joule, plus 12 Newton meters, which is a joule, plus 0. That would be the total work done in that particular example, with that specific force and that specific displacement. So there's 2 ways, basically, to find the work. If you know the magnitude of the force and displacement and the angle is given, or really easy to find, just do it that way, that's fine. But if you're given forces and displacements that are a little more complicated in that it's going to be harder to find the angle, just do the actual dot product. Multiply the x components, multiply the y components, multiply the z components, add it all up, you got your work. Now, by the way, now that we have this, it would be easy to find the angle between these two. Right? We know this is 18 joules. We can find the magnitude of the force using the Pythagorean theorem. The Pythagorean theorem works three-dimensionally. We can find the magnitude of the displacement from the Pythagorean theorem. So we can find F and D. We already know what the dot product is. It's 18 joules. So we could easily find the angle now if we wanted to know what it was. Easy to work backwards. So technically, that's what we were doing. The examples we did with work, we were technically doing the dot product. You just didn't know it yet. The whole reason, friction, the work done by friction was negative, why we put a negative sign on it, is because the friction was always opposite the displacement. The angle between the friction and the displacement was 180 degrees. That's where, mathematically, that's where the negative side comes from. Okay? It's because of the cosine of 180. So there's nothing wrong with what we've done. This is fine. Just find the component of the force parallel to the displacement, you're good. If you're given vectors and you don't feel like finding the angle, then do the dot product to find the work. It works just as easily. Okay? the other way to multiply vectors, when we get to chapter 12, it's called the cross product. It multiplies perpendicular components and gives you a vector answer. It's not too hard to do though. So.